Realistic human body models are essential for many graphics, ergonomics, and computer vision applications. The most realistic models are learned from data, but are not compatible with existing rendering engines. Models that are compatible either lack realism or require extensive artist effort to create. In contrast, our skinned multi-person linear model, called SMPL, is learned from data, realistically represents any body shape in any pose, is more accurate than recent methods, and is compatible with existing graphics pipelines. SMPL is compatible because it is based on standard skinning methods. A skinned body model defines the vertices of a template T in a rest pose, joint positions J, and blend weights W. Given the pose of the skeleton, theta, skinning computes the vertex locations of the mesh, using linear blending of the vertices based on rotations of different parts. Standard skinning functions, M, include linear blend skinning, denoted by LBS, and dual quaternion blend skinning, denoted by DQBS. Both have well-known artifacts, highlighted here. In contrast, SMPL is a blend skin model with blend shapes that are learned from training scans. The influence of each blend shape is automatically computed from the pose of the body. These blend shapes correct standard skinning errors and capture pose-dependent shape variation. SMPL contains a template mesh T in a neutral pose, and adds offsets to this template to represent new body shapes and pose-dependent shape changes. From training scans, we learn shape blend shapes that capture the variation in human shape. Adding different combinations of shape blend shapes produces different body shapes. SMPL predicts the joint positions for a given body shape as a function of the mesh vertices. These are shown as white dots. From training scans of people in many poses, we learn pose blend shapes that capture how real bodies differ from blend skin bodies. Given a pose, SMPL computes the linear contribution of these blend shapes that correct skinning errors and that produce realistic pose-dependent deformations. Finally, SMPL uses standard blend skinning to transform the deformed template shape into the desired pose. Note that the contribution of the pose blend shapes changes with pose. All these steps are standard, making the SMPL model compatible with existing animation pipelines. Our formulation allows us to learn all parameters directly from data, producing a model that realistically represents any body shape in any pose. To learn the SMPL pose model, we use a database of over 1,700 3D scans of 44 different subjects in a wide range of poses. From these we learn the blend weights W, and a function that predicts the location of each joint J, using a sparse set of mesh vertices. We also learn the pose blend shapes B sub P that are added to the template to model how people deform with pose. Here we see a SMPL model animated on the left, and the associated pose blend shapes applied to the static mesh on the right. Notice how the static mesh deforms, particularly at the elbows, shoulders and hips, to compensate for the soft tissue deformations that occur due to pose. The pose blend shapes, P sub I, are linearly combined and added to the template vertices. A key novelty of SMPL is that the coefficients, F sub I, correspond to the elements of the part rotation matrices. This formulation is important for good results. On the left, we showed blend shapes predicted directly from joint angles, theta. This naive approach produces serious artifacts. On the right, we show simple blend shapes predicted from elements of rotation matrices. Please see the paper for further details. We learn shape blend shapes from approximately 4,000 body scans from the US and European CSER datasets. Critically, our formulation estimates the pose of these scans, effectively factoring out pose variation from the body shape model. We estimate an average template shape, and use principal component analysis to estimate the directions of maximum shape variation. These are our shape blend shapes. Here, we show the first few principal components of male and female body shape. The shape blend shapes are linearly combined and weighed by the shape coefficients beta. The result is offsets that, when added to the base template, give a new body shape. The joint locations are predicted from this body shape. All the blend shapes are simply displacements from the template, and, once summed to produce a deformed body shape, the skinning equation is then applied. SMPL allows the independent modification of pose and shape. This is similar to previous models like SCAPE, which are based on triangle deformations. SMPL can be built using different skinning functions. We train SMPL models using linear blend skinning, shown on the left, and dual quaternion blend skinning, shown on the right. For both, we show the pose blend shapes that are applied to the base mesh. SMPL is more accurate than a blend SCAPE model, trained from exactly the same data. Since they are based on triangle deformations rather than skinning, SCAPE models are incompatible with existing animation systems. While realistic, SMPL does not model soft tissue dynamics. The center mesh shows our template registered to 4D scans. The differences between SMPL and the dynamic registration data are shown in the base pose on the left and correspond to soft tissue dynamics. We extend the SMPL model to add dynamic blend shapes, B sub D, to the base model. The dynamic blend shapes are learned from a training set of 40,000 dynamic scans, and like the other blend shapes, are simply offsets to the vertices of the base mesh. The linear coefficients that modulate the dynamic blend shapes are a function of the history of poses, capital Phi, and the body shape parameters, beta. We call the resulting dynamic multi-person linear model dimple. On the left we see the standard pose blend shapes of simple. In the middle we see the dynamic blend shapes of dimple, and on the right is the final dimple animation. Since soft tissue dynamics depends on the composition of the body, the contribution of the blend shapes varies with the body shape defined by beta. Please see the paper for details. Dimple is comparable to our previous Dyna model, which is based on triangle deformations. Dimple results sometimes look dampened compared to the ground truth registered meshes. By simply exaggerating dimple predictions, we obtain an animation that is close to the original registered meshes. Because they are based on standard blend skinning, Simple and Dimple are compatible with current rendering engines. We export Simple as an FBX file that can be loaded into standard graphics software. A version of Simple is freely available for research purposes. We provide simple scripts for Maya and Unity that generate the linear blend shape coefficients given the body pose. Despite its simplicity, we obtain an accurate model by learning it from thousands of 3D scans. Dynamic blend shapes increase realism and make animations more lifelike. Dimple further demonstrates that Simple is a general framework that can be easily extended.